Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Hi everyone. Welcome to the session on malware detection and protection. My name is Patrice Godefroid and I'm a principal researcher here at Microsoft Research. And so malware detection and protection remains a rich topic of research as well as a significant challenge in practice. And I've invited two world-class experts on this topic, Professor Dawn Song from UC Berkeley and my colleague Ben Lifshitz from MSR. And I've asked them to present an overview of their work and of their views in that space. So this session will consist mostly of two talks, and the first one is given by Dawn. So Dawn is an associate professor at UC Berkeley in the CS department. And before joining Berkeley, she was an assistant professor at CMU. And her research interest lies in security and privacy issues in computer systems and network, including areas from software security, networking security, database security, and distributed system security, and ranging up to applied cryptography. She is the recipient of numerous awards. And thank you very much for being here. And I'll give you the floor. Thank you.
Thanks a lot, Patrice. Thanks, everyone, for being here. My name is Dawn Song from UC Berkeley. So today I'll talk about malware defense, new trends, and approaches. So as we all know, malicious code is posing critical threats on the internet. They are growing exponentially and has been causing huge amount of financial damages. So in this talk, I'll mainly look at two parts in the landscape. The first part, I'll talk about the emerging threats in malware, and then second, I'll talk about some of the new approaches that we can employ for defenses, and mainly using some of my own work in this talk as examples. So first, malware, as we are all familiar, has been causing all these issues, and now malware is entering new domains. So many of you have seen Android malware, and also with the Stuxnet, the malware is even going to critical physical systems, and also with the cars being more and more driven by software and being connected over the network, that gives new chances for attackers to attack as well. So one main message I wanted to send in the first part of the talk is that now the world is being more and more connected, and malware is entering new landscape as more parts of the world gets connected. So first we'll look at one example domain, which is networked medical devices. Medical devices are becoming more and more networked. For example, now you have these smart insulin pumps which receive signals over wireless to decide how much insulin to drip into the patient's body. And also these medical devices are becoming more and more sophisticated in terms of software. They're being controlled by software, and the software actually has been playing an increasing role in device failure in the past decade. And also, another interesting thing about medical devices is that even though in security we all know that monoculture is a really bad thing, unfortunately in medical devices, hardware and software is usually a monoculture, and this makes security threats even more severe. So in our work, we did a case study for AEDs. So these are defibrillators, and AEDs, the deployment of AEDs has been increasing dramatically over the past decade. Now there are over 1.5 million devices deployed all over the US. And unfortunately, with so many AEDs being deployed, still many AEDs, even now talking about attacks, just failures. There are now, for example, over 28,000 device failures reported in the last, recent years. So in this work, we took a case study of one particular type of AED device, the cardiac science AED device. And the main question we wanted to look at is, given that there hasn't been much work before looking at the security analysis of medical devices, we wanted to take the first step towards looking at whether these medical devices are vulnerable and whether, for example, propagating malware such as worms or viruses are possible in this space. So that's the main question that we set out to find the answer for in our study. So in this study, we took this AD device and we got its firmware and also related other software components that runs on PCs as well to facilitate the operation of the AD device. And we performed a number of different types of analysis using a combination of both manual binary reverse engineering as well as using automated binary analysis using our own binary analysis infrastructure, the BitBlaze binary analysis infrastructure. We performed binary analysis on the firmware and the other facilitating software that I mentioned, and we found a number of vulnerabilities in this AD device. And by combining multiple AD vulnerabilities that we discovered, we are able to show that, one, the serious security vulnerabilities do occur in these medical devices, and two, actually you can launch propagating viruses and worms. So this is how the one possible attack could work. Is that so? One vulnerability we found is that for the AED, the AED takes firmware updates. However, the firmware updates is only verified using a custom CRC code, and we were able to automatically. We were able to reverse engineer the CRC function, and hence we're able to craft any new updates, new software firmware updates for the AD device, and then compute the correct CRC code, and hence we can update the AD device with any arbitrary firmware that we wanted to upload. So that's the first vulnerability. And the second vulnerability is that the AD device often needs to be updated, software updates. And when it connects to a machine to get software updates, there is a number of handshakes going on. And unfortunately, the machine which is doing the update with the device, it receives some information from the AD device, but it does not do the proper input checks. And hence, there's the famous the famous buffer overflow vulnerability occurs, and we can exploit this buffer overflow vulnerability and enables arbitrary code execution. So when you put the two vulnerabilities together, then as a first step, we can use we can upload a malicious firmware into the AD device, given that we can compute the custom CRC function. And then once this AD device is compromised, now when the AD device is being connected to, for example, the safety officer's laptop for further software updates, now this malicious AD device can then now automatically compromise the computer which is supposed to be doing the software updates. And hence this computer gets compromised, and now when this computer is used to connect to other AD devices for doing software updates for these AD devices, now these other AD devices gets compromised too. So as you can see, by combining a number of vulnerabilities that we discovered in the AD device, now we can essentially enable a worm that essentially propagates through the networks of devices. So this is just one simple example showing that, one, in medical devices, serious security vulnerabilities do exist, and two, they can be used to construct these, for exploits for arbitrary code execution, and also to automatically propagate through the networked medical devices. And this is just the first step. And now, as we talk about Internet of Things, more and more devices are being connected. For example, the Niagara framework now helps connect millions of devices, which controls your lights, your AC, and also controls wastewater systems, and all sorts of different physical devices. And this is only the first step towards this connected Internet of Things, where malware can even do more harm. So that's how, as we connect more and more devices, malware can go into new landscape. And now, as a second example, I'm going to show you some more, maybe a little bit even more scary landscape where the malware could potentially enter. And this is another piece of work that we did recently. So another trend we are seeing is that these brain-computer interface devices are going to mass market. You can buy for $300 of these devices. These are essentially consumer-grade EEG machines where you wear these headsets on your head, and then you will the headsets will be monitoring your brain signals. And there's a whole new ecosystem emerging using these headsets, and they have their own app market. So developers can develop various apps running on these devices by taking signals from these devices. And from $5 to about $100, these apps they promise to help you with better sleep, better meditation, even math trainer, or playing various games. So the question is, given that these brain reading machines, devices are becoming more popular going to the mass market, what may happen? So for example, all these apps on the app market, what if an EEG gaming app actually is malicious? So as the user is playing supposedly a fun game, it's using its brain to control whatever the mouse movement and so on, but actually the app is actually secretly reading your mind. Can this happen? So this is the work that we did recently. So just one quick explanation. So how do these devices work? Essentially by presenting to users stimuli, user's brain will essentially respond to stimuli. And also the interesting thing is that often these stimuli the users cannot control. They will be spontaneous. And in particular case, this is very useful for attackers. So with these, essentially these are called event-related potentials, ERPs. So as users are presented the stimuli, the brain will respond to various stimuli in different ways. And hence, one question is whether attackers could craft certain stimuli such that the attackers can then read your brain response and learn, for example, sensitive information about you, reading your mind. So that's the experiments that we set out to do. So the key question that we wanted to answer is whether the signal captured by a consumer-grade EEG device can be used to extract potentially sensitive information from the user's brain. And in this experiment, we actually perform experiments with about 30 computer science students. Each experiment actually lasted for about 45 minutes. We did a number of experiments for each person, and each experiment lasts about only 30 seconds. So the experiment essentially goes with, given as I mentioned that as users see stimuli, their brain will respond. And so we have, for each person, we have the training session and we have the testing attack session. So in training session, we'll show certain stimuli that we know that the user will respond. For example, a photo of Obama, or we let the user look at screen counting numbers and so on. To train, provide the training set for us to essentially understand how to decipher users' brain response. And then after that, we present to the user a number of testing stimuli, such as attack stimuli, where we didn't know what the user's answer would be, and then in the end, from the learned classifier, trying to predict what we have learned from the user's brain. And in this experiment, we essentially presented different types of stimuli to the users, and the question here, essentially, we wanted to check is whether, for example, we could learn user's pain. For example, the various digits of user's pain, whether we can learn that whether the user knows a certain person with the photo shown, whether we know which bank the user uses, and which month the user was born, and where the user lives. And essentially, we constructed the experiments and presented users different types of stimuli. And in the experiments, this is the experimental results. which showed that for all the experiments, all these different types of information, we were able to do much better than random guess. And hence, the answer is that even with these consumer-grade EEG machines, EEG devices, we can actually, attackers could construct potentially malicious games or applications to try to steal sensitive information from the user. So that's the first part of the talk, is that as we see that more and more parts of the world get connected, including our own brain, the malware could enter new parts of the landscape. So what can we do to defend against all these new threats and so on? So the second part, I'll talk about defenses. In particular, talking about various new approaches for defenses. So when we talk about defenses, we can look at the different types of defenses. So traditionally, I think a lot of the security community have been focused on I would call reactive approaches. And many of these approaches can be very effective in terms of helping us to detect known classes of malware, for example, and to detect new occurrences of even previously unknown malware. So, for example, in my own work, with my research group, we have developed this bit-based binary analysis infrastructure where we develop different types of malware detectors to detect different types of malicious behaviors. And also in our recent work, joy-based analysis infrastructure, we developed different tools to detect different types of malicious behaviors in Android apps, vulnerable behaviors in Android apps. And also Ben is going to talk about his great work in the Zozo series for detecting malware. So in this talk, I won't go much detail into this type of approach, especially given that Ben will give you a great talk as an example of this category. In this talk, in terms of defenses, I will focus on two maybe less studied areas. So in terms of malware defense, one is I call it offensive approach, and the other one is proactive approach. So for offensive approach, the key question here is that attackers, the way they launch their attacks is by finding vulnerabilities in benign systems, in our systems. So the question is whether we can flip it around, whether we can actually find vulnerabilities in malware, and hence instead of having attackers attacking us, by finding vulnerabilities in malware, we can go attack the attackers. Right. So that's the essentially the key question that we wanted to look at in this type of approach, the offensive approach. And in particular, we wanted to know that whether malware has vulnerabilities too, or whether given that they do such a great job finding vulnerabilities in our benign systems, they do so well, they don't have vulnerabilities. And also, how do we find vulnerabilities in malware? And in particular, this type of approach can provide a new type of arsenal for us to combat malware. For example, it can, once we find vulnerabilities in malware, it potentially can help us to automatically clean hosts, can help us understand better malware genealogy, and also help us with botnet infiltration and takedown, and also certainly be an important arsenal in cyber warfare. So again, using examples of our own work in this space, I'll give you two examples. The first example is about finding implementation vulnerabilities in malware. Essentially, for example, attackers have routinely found buffer overflow type of vulnerabilities in our benign systems. What about malware? Do they have buffer overflow issues as well? So we, again, using our binary analysis infrastructure bit-based, and also using some new dynamic symbolic execution techniques that we have developed, we were able to perform essentially automatic exploration of the program execution space of different real-world malware. And the answer is by analyzing these different real-world malware, we were actually able to find different types of security vulnerabilities in the implementation of the malware. And also, the interesting thing is that we found that vulnerabilities in malware actually they persist across different revisions. For example, some of the malware, the vulnerability in malware actually has been in the malware over 2 years, and it has persisted across different revisions and so on. So this also this shows that also vulnerabilities in malware can help serving to provide information for malware genealogy as well. So that's one example of finding implementation vulnerabilities in malware. Another question is whether we can find even higher level vulnerabilities, for example, vulnerabilities in the design of malware protocols. So here is in another work that we did. We looked at examples of real-world botnets. These botnets, essentially, these are, they can be millions of zombie machines that are controlled by the botnet servers. They communicate with the botnet servers over what we call botnet command control protocols. And the question is whether we can find vulnerabilities even in these protocols and how these vulnerabilities can help us in defending against malware. So this is one real-world study we did, is by actually analyzing a real-world botnet called Magadi. And in particular, in the Magadi botnet, at one point it accounted for over 90% of the spam sent over the entire internet. So what we did here is that by, again, using our bit-based binary analysis infrastructure and also some of the new machineries that we built, we were able to automatically, essentially what we call performing protocol inference to learn about the botnet command and control protocol for the Magadi botnet. In particular here, for Magadi, given that the functionality it provides is fairly sophisticated, so it actually has a different number of different types of servers that the bot would actually talk to. For example, the template server, the master server, and the SMTP server. So I won't go into the details of how we actually perform the automatic protocol model inference. So we developed an automated system that would talk with the real-world botnet CNC server using our bot emulator, and combined with a learning infrastructure that we have built and talking over the anonymous communication system Tor. We were able to automatically extract the command control protocol of the Magadi botnet. And here I'll just give you a few sample applications of how extracting this information and finding vulnerabilities in the botnet CNC protocol for the botnet protocol help us with the different applications. So the first one is often that we want to disable a botnet. So one question for disabling botnet is to identify critical links, meaning that if we want to take down botnet, there may be a whole bunch of different servers that the bots talk to. Which links should we cut? Which machines should we take down to reach the best, the most benefits? And we call those links critical links. So by identifying, automatically extracting the CNC protocol from the real-world botnet, we were able to identify what are the critical links for this Magadi botnet. In particular, even though there are so many servers that the bots are connected to, we were able to automatically identify that if we just take down one Magadi SMTP server, then we can stop all the bots from spamming. So that's the first application, and we verified that through experiment. The second application is that once we know how the CNC protocol works, we were also able to identify automatically, essentially performing fingerprints. So as I mentioned, the Magadi also has, among the different servers, one type of server is SMTP server, where essentially the bot implements its own SMTP protocol. However, from extracting the protocol automatically, and also we were able to, using the same a technique, we are also able to automatically extract the SMTP protocol implemented in a popular implementation, postfix SMTP. And then by comparing the two state machines, we're able to automatically identify the difference between the two state machines. And hence, this difference essentially forms the fingerprint of the MegaD SMTP server, meaning that now by using this difference, we can automatically tell that this is a MegaD SMTP server instead of, for example, a benign postfix SMTP server. So the third application is that we were able to also identify some design flaws in the CNC protocol. So by analyzing the state machine of the CNC protocol of MegaD, we were able to identify that for the bot, in order for the bot to actually obtain the spam templates, it needs to go through along this red path, because the attacker wanted to do certain verification. However, because of the design flaw, we were able to automatically identify a much shorter step for the attacker to obtain the spam template, and hence we can completely bypass the check that the attacker intended to do. And by using this technique, we were able to also perform further work to automatically obtain spam templates for further studies. So these are our examples demonstrating essentially this offensive approach can be very powerful in combating malware. They can help us to identify vulnerabilities in malware and help us to figure out what's the best way to take them down, to clean them up. So the next domain I'll talk about is now, so this helps us to fight the malware. And then a key question is, yes, so now people may talk about it that we are in this cat-mouse game. We do something, then the attacker, changes the strategy and finds the next weakest link and try to attack, and then we have to do something else. So the question is whether we can actually employ a proactive approach such that it really help us to build systems that are secure, so that we can build a secure foundation, that we can build more secure application and systems on top, such that we can get out of the cat and mouse game. So that's what I will talk about next, is this in terms of what can we do to get out of the cat and mouse game, taking this proactive approach. In particular, I'll give 3 examples, and they all fall into the same essentially theme, as what I call by building new security primitives. By building different types of new security primitives, help us to essentially build a solid foundation to help us build more secure systems and applications on top. So the first example I'll give is how can we design new security primitives such that it helps us to build secure systems even when the machine has already been compromised. And I'll give an example called the cloud terminal. That's a new security primitive that helps us to essentially get secure access to cloud applications. And the second example I'll give is how do we build new security primitives that help us to build secure applications by design. And as an example, I'll talk about our new work on context-sensitive automatic sanitization of web templates. And finally, I'll talk about our new work in privilege separation in HTML5 as an example of new security primitives that help us to have a better security architecture and better auditability. So the first example I'll talk about, as I mentioned, is the cloud terminal. The question is that the goal is that now we are, the cloud computing is here. We run a lot of cloud applications. We have a lot of sensitive data stored in the cloud. And we can do a lot of things to help us secure things in the cloud. But however, still we need to be able to access those cloud applications and also the sensitive data stored in the cloud. Unfortunately, our devices, our laptops, desktops, those are the places in particular where malware may reside. So the question is, what happened? So even if our devices, such as laptops and desktops, are compromised, can we still have a security primitive such that will help us to build a trusted path into the cloud application? So that even if, for example, your laptop is compromised, but still using your compromised laptop, you can still have a trusted path into the cloud such that you can perform your sensitive security operations, look at your sensitive data in the cloud, but not worrying that the sensitive data may be stolen by the malware on your laptop. So that's the goal. Right. So to aiming at addressing this issue, we developed a new system called the Cloud Terminal. And this is the Cloud Terminal's architecture. So the idea is essentially, given, for example, your laptop or your desktop, that we have this that has trusted, essentially, for example, has the trusted computing capability, for example, with our TPM. So what we do is that we build a microvisor. It's a really, really thin hypervisor that runs directly on top of the hardware. And the advantage of this microvisor is that it can be securely installed even if your machine has already been compromised. But we can still securely install it on your machine such that, and we can also attest that it has been securely installed. And then on top of the microvisor, we run a really thin, what we call the Cloud Terminal client. And this whole thing forms the secure thin terminal. And in the Cloud Terminal client, we do something really, really simple, which essentially is kind of like the VNC client, where it can display the images and can take your keystroke and mouse events. And the information essentially will be then sent to the cloud application running in the cloud over encrypted channel. And the cloud application will receive the various keystroke and mouse events, perform the execution, and then return the display to the client. So this is the Cloud Terminal architecture. So with this Cloud Terminal architecture, it enables us to essentially have a trusted path into the cloud applications with a number of new advantages that previous approaches couldn't accomplish. As I mentioned, this approach, we can install it on a machine which has already been compromised. And also, even if the machine has already been compromised, we can ensure, given the trusted microvisor and also the thin client, the Cloud Terminal client, we can essentially support generic applications. Any applications that runs in the cloud, we can actually support. And also we provide fine-grained isolation. And really, with this approach, we have really, really small TCB, trusted code base. In this case, we have only 22,000 lines of code. And through attestation, we can really ensure that the system is properly, is securely installed. So as I mentioned, for example, the trusted code base is really small. And also we performed experiments with a number of different applications that we ran in the cloud. And the performance overhead, we showed that the performance overhead is fairly low. And also the approach can be highly scalable. So that's one example of new security primitives for building the trusted path into the cloud. So the next two examples I'll give is essentially help answer the question, how can we essentially develop new techniques and these new security primitives that help us to build secure applications and systems by design. So, so the first one I'll talk about is essentially how do we do auto-sanitization of web applications. Web vulnerabilities have been increasing, have been growing, and now they have overtaken the lower level vulnerabilities. So the question is, including our own work earlier, we have developed techniques and tools to try to find these different cross-site scripting vulnerabilities in real-world web applications. But however, one challenge is that we may never be able to find and fix all these cross-site scripting vulnerabilities. So how can we do better? For example, can we build web applications that, from the start, that are free of cross-site scripting vulnerabilities? So, so this is, for people who don't know about cross-site scripting vulnerability, this is a very quick refresher of the cross-site scripting vulnerability. It's essentially the, for example, this is a client-side cross-site scripting vulnerability where the user is going to a website which loads JavaScript from the client side. The JavaScript will try to read some essentially some parameters from the URL and then use it to compose the actual HTML. For example, in this case, to try to load the user's profile page. So this is when the application runs in a benign way. But however, this has a cross-site scripting vulnerability, in which case, if the attacker, instead of, because the JavaScript code here actually is not sanitizing the parameters at all, so in this case, the attacker can construct a malicious URL such that when the user clicks on this malicious URL, then the attacker's embedded JavaScript actually gets run instead of loading the user's profile page. So that's a quick refresher of the cross-site scripting vulnerability. And here, the key issue here is that cross-site scripting vulnerability happens when the structure integrity of the document is violated. So what you see as the original intended structure is now becoming the actual structure where the attacker's code actually gets loaded instead of the images. So the goal is to actually essentially establish a method to enable structure integrity. And this is a very common class of issues. So due to time limit, I won't go into the details. So the solution here is, the typical solution is that with, for example, web templating language, you can define the web templates, and also you can leave these holes. And then the parameters essentially are the variables get filled into these holes. And the key question is, we want to ensure that these holes are being properly sanitized. In particular, here, when a parameter is being put into the hole, we want to ensure that before they are being put in the hole, they are being properly sanitized. Right. So for example, you can use different sanitizers to sanitize these parameters. So in terms of challenges for this sanitization method, one key challenge is that even if you have correct sanitizers, but still you may have missing sanitizations and you may have incorrect sanitizations. So picking the right sanitizer is actually can be very challenging, because which sanitizer to use, it depends on the context. In HTML, you may have many different contexts, and for this, for example, different URL contexts and tag contexts and so on, and you have to use different sanitization routine for different contexts. And people have done study showing that in real-world applications, even when people try to do manual sanitization, they often pick the wrong sanitization routine. So in our solution, essentially, we developed an approach to perform automatic sanitization. And and in particular, context-sensitive automatic sanitization. So the idea is that instead of having users to manually figure out what sanitization routine to put in, and then manually insert those sanitization routines, we develop a new method using automatic type inferencing to automatically infer what is the right what is the intended context and what is the right sanitization routine to put into the whole to enable automatic sanitization of web templating languages. So due to time limits, I won't actually go into the details about this, but the high-level idea is that we developed a new essentially time framework. In particular, we introduced a new concept of type qualifiers. So these type qualifiers essentially represents the context that this variable is safe to be put in. And then by developing a number of typing rules and also the type inference algorithm, we can then, by analyzing application written in a web templating language, we can do automatic type inference to figure out. Essentially, we instrument the compiler stage, and in the compiler stage, we perform this type inferencing to figure out what is the context of the host, where the variable should be, and also so to automatically figure out what's the right sanitization routine that the variable should be sanitized with. So essentially by using type inference to decide where to put in the sanitizers and what sanitizers to put in. So we did this work in conjunction with joint work with Google, and we implemented our approach into the Google Closure template, which handles a number of more advanced features. And our work now has been in the Google Closure, and now if you are using these Google apps have been secured using essentially these auto-sanitization routines. So the approach has been adopted, and now a lot of the Google applications have been secured using this approach. So that's one example showing that instead of trying to find these different cross-site scripting vulnerabilities in real-world applications, we develop a method to once for all, if you use these web templating languages, now the application developed using these web templating languages are now secure against cross-site scripting vulnerabilities. The final example that I will quickly give is how to build new security primitives to help have a better security architecture and with better auditability. And this is doing privilege separation in HTML5. So one issue we have today is the web application is getting more and more complex, and they are becoming huge. Sometimes they can have even megabytes of web application code. So one issue is that all this web application code, they have one security principle with ambient authority. So essentially, the entire application runs with the origin of the web application with the same privileges. So let me here just give you one example of something called awesome screenshot. So the awesome screenshot web application has two main components. One is that it can take a screenshot. Once you hit the button, it takes a screenshot. And another part is that once you take the screenshot, it also has an image editor capability, so that you can do various things to edit the screenshot. And so this application has half megabytes of code. And what kind of permissions does it have? Essentially, it gets all the data on all the websites that you visit. And this is half megabytes of JavaScript code and half megabytes of trusted code base of JavaScript code. So this has two issues. One is a bundling issue. It's one origin, but actually it's two applications. You have the screenshot components, which can save files, but doesn't need to. And also you have image editor components, which can take screenshots, but doesn't need to. And this is not the exception. 19 out of top 20 extensions that we studied exhibit this behavior. The second problem is what we call TCP inflation. So now all the code runs with full privilege. But unfortunately, only the core application need to. And if you look at these half megabytes of TCP, they have 500 kilobytes of generic libraries like jQuery and so on. And also, this is not the exception. We measure the fraction of functions that requires privileges. We analyzed the top 50 Chrome extensions and showed that about 50% of the extensions, only 5% of their functions actually require privileges. And about 80% of the extensions, less than 20% of the functions require privilege. So our solution here is developing a new security primitive called privilege separation, where instead of the whole application has all the privileges, we have a privileged parent which has privileges, and we divide the client into different components. And the components will talk to the parent to request for privileges, and the parent has a policy controller which controls whether it will grant the clients with privileges. So this way, only the parent runs with privilege, hence we have huge TCP reductions. So I'll skip the details since we are short in time. I'll just show you the actual some case studies. And also here, to ensure the security, parent, we have a few invariants that we ensure with our security primitives, such that the parent cannot convert string to code, the parent cannot execute arbitrary code from the web, and also the parent is the only entry point for into the privilege origin. And only primitive data types can be passed across the privilege boundary. So with our application here, for example, with awesome screenshots, we were with our privilege separation method. Now the reduced TCP is only 16 kilobytes, and actually we almost didn't need to change any lines of code, not counting our own like shim code that we added, but just for the application code, we almost didn't need to change anything. And also we looked at some other applications such as source kits, SQL body. So here you can see orders of magnitude reduction in the trusted code base. So in summary, privilege separation in HTML5 is a new security primitive. And now we're actually collaborating with Google. This has inspired Google in terms of developing their secure web applications. And this can essentially provide a standard abstraction to help people to build more secure applications on top. And also we show that to retrofit applications is fairly easy. So in summary, in this proactive approaches space, I've shown you a few examples, essentially demonstrating, demonstrating that an important area that we need to do more research in for defending against malware attacks is how we can develop these proactive approaches such that we can build secure applications and systems by design. So in conclusion, in this talk, I showed first that malware is entering new landscape as more parts of the world, and also including ourselves, becoming connected. And also, in terms of defending against malware, we have these different types of approaches. A lot of great work, including what Ben's going to talk about, has been the reactive approaches area. And more work, I think, can be done in the area of offensive approaches and proactive approaches. Thank you.
Thank you very much.